welcome all of you to the annual CRM-Fields-PIMS prize lecture to be given this year by Professor Stevo from Todorcevic, the University of Toronto. The prize lecture this year is a really special event for us because Stevo has not only been very active in his institute's programs over the years, but he's also one of the organizers of our current thematic program on forcing and its applications. My name is Ed Bierstein. I'm the director of the Institute. Let me just say a couple of words about the prize. The CRM-Fields-PIMS prize has become the premier Canadian award for research achievements in the mathematical sciences. It was first awarded in 1995 as the CRM-Fields Prize, and in 2005, PIMS became its current version. The prize winner is selected each year by an international committee with representatives chosen by each of the three institutes. The prize includes a monetary award, and it involves the prize winners giving a lecture at each of the three institutes. I'm going to call on Justin Moore, who is also an organizer of the Forcing program, to say a few words about Stevo. But beforehand, I would like to mention the sources of support that make the Institute's programs possible. We receive major research funding from the Ontario Ministry of Training Colleges and Universities, as well as from the Natural Sciences and Engineering Research Council of Canada. We're also generously supported by 7 principal sponsoring universities in Ontario: Carleton, McMaster, Ottawa, Toronto, Waterloo, University of New York, as well as by a growing list of affiliate universities in Canada, the United States, and more recently Europe. We're also supported by several commercial and national partners. Following the lecture this afternoon, there will be a reception in the atrium that you're all cordially invited to come to. I hope you enjoy the lecture, and Jeff is going to say this.
I will try to keep it short, but I found this is a tricky task. So I guess in full disclosure, I was Stevo second student. I came to know him in '96. I just want to give a brief history of Stevo's bio first. So Stevo completed his PhD in 1979 under Euro Grepa. He then traveled around quite a bit. He was a postdoctoral fellow at Dartmouth, a Miller Fellow at Berkeley, and then an Ullman Chair at the University of Colorado, Boulder. He's been a fixture at Toronto since the 90s. And in 2004, he became a kind of a research chair. Prior to that, he was also became director of research at the CNRS in Paris, affiliate with Paris 7. In '98, when I was still a student studying under him, he gave a talk at the ICM, and this is sort of very memorable to me. I remember poring over his article and found it very inspirational. And actually, I went on to solve many of the problems that he wrote about in that article. That was sort of one of the things I've come known for. I think that anyone who knows Stevo would describe him as a very intense person. He has a deep passion for mathematics, and I mean, in a sense, he's a step away from Erdish in the extent to which he sort of devotes his life to mathematics. He has a minimal life outside of mathematics, and it's just purely devoted towards proving theorems. He is also, everyone who knows him knows that he's a sort of a perfect example, from a Hungarian proverb that a mathematician is a machine preparing modeling theorems. Probably the best example I know of that. He sort of, I think one of his greatest accomplishments was to realize the extent to which Ramsey theory is important. I think that we know set theorists realize that he's kind of revolutionized our thinking of how its role within set theory and its role within the rest of mathematics. I think this is only going to be realized more in the future outside of set theory. He's used it to, in many cases, isolating it as the key core difficulty of a problem in an application. He's used it to complete his raw classification program, structure the side L1. He was instrumental in illustrating his role in topological dynamics as it relates to the actions of automorphism groups, connecting the structural Ramsey theory, which was developed in the 70s, to fixed point theory. And he's also, I think, has one of the most open-minded views of how forcing can be used. His Journal AMS article where he exhibits how you can use the method of forcing to prove theorems in ZFC is really eye-opening. And I think it's always intrigued me whether someone could learn forcing by reading that paper. If you know some analysis, if you don't know forcing, I would maybe encourage you to take a look at this paper. And now we're going to come back to one of his earliest discoveries. And when he won the prize, I was sitting at the table next to him, and I asked him, what are you most proud of? What result are you most proud of? And he said his method of minimal walk. So without further delay, let's hear from Stevo.
Thank you, Ed, and thank you, Justin. I thank the Tree Institute for giving me this prize and opportunity to present some of the work which I had done. This third lecture is a natural in this progression of lecture, which is moving towards finite to an infinite and eventually to set theory. So if one, I don't know whether the slides of the previous talks are available, but you'll see there's a very natural progression. Is indeed there is some Ramsey theoretic view to various area. In this case, in this context, I go towards set theory, and this is where this technology, which actually works on some kind of technology, which is helping us to recognize this extent of the Ramsey phenomena in set theory. Okay, so okay, I will. This is the rough overview. Well, I would like to spend some time with initial motivation, because this is, even among set theorists, not well known. This is the classical notion of walk and the walk which I discovered in order to solve one of these problems in initial motivations. And then there are various development. And one of the point is a kind of a use why one is doing this is to find canonical objects. And I decided to illustrate it in three cases. You have you see is to find a canonical tree and canonical in order and canonical ultrafilter. Maybe even 20 years ago probably would be very difficult even to imagine, in the sense that these objects are so in such a large profusion that. And all of them look so similar that you would perhaps almost think this is contradictory, expecting there will be something canonicity in such a wide spectrum of objects. For example, linear orderings, basically such a simple structures that you can very easily vary them, so all of them tend to look the same. And why suddenly there is such a canonical tree, and canonical ultrafilter is even more, perhaps. This is the latest one, maybe surprising. Okay, so that's the overview. Okay, so the initial motivation is really always everything seems to be, at least what many things which I was trying to do somehow relates to this form of a Ramsey theorem, which is not so frequently stated. So Ramsey was interested indeed to solve some basis problem. He was interested to classify relational structure on the integers. He needed to know how they look like, but in some not global sense, but in some local sense. And you are looking at the restriction, and the restriction here, rather than globally. So your arbitrary structure, when you restrict it to a large set, and the large set basically something isomorphic to the original structure. I mean, that's a notion. We can vary this notion of largeness. That was the original theorem of Ramsey. And it is for that purpose that he invented his Ramsey theorem. But at that stage, basically, you like to ask whether the same thing can be done in other contexts. You can either add a structure, or you can add change the cardinality. Both of these have been dealt with. People have a looking at contexts. You're adding a structure or integer. For example, you want to change integers with the rational numbers, real numbers, or you want to change the countability by a first uncountability, second, third, etc. So it's a very natural questions. At this stage, they are rather formal. You will see later, actually, they're less formal than they seem to be quite important. And I wanted to point out the more typical case. Ramsey realized that to classify arbitrary relation, all you need to do is to classify equivalence relations. So later on in combinatorics, this theorem moved. They changed the terminology. In combinatorics, this is usually considered colorings, say finite colorings, rather than equivalence relation with finite quotients. So basically, he was saying there is only one, namely the full relation. So every relation, every equivalence relation on this omega to the k is a typical symmetric cube. So in order to avoid some trivialities, k tuples are typically increasing, so you don't want to deal with the permutation group on k. You can if you want, but I think that you are saving some. This way you are saving some trivialities. Okay, so that's the original Ramsey theorem. And I just wanted to point out that you see the equivalence ratio of the finite quotients. Todorcevic were able actually to list them exactly arbitrary ones. It's interesting, although as I said, this actually follows from the Ramsey theorem itself. The finiteness of the list follows from the old Ramsey theorem, but here you have actually explicit list, and sometimes we are really actually interested in these lists. Because in the applications, you like to know actually how the equivalence relation looks like. And basically, what the equivalence relation is a projection, induced by a projection map on these coordinates. So if you look at the equivalence relation of symmetric cubes or countable infinite sets, the modular restriction on a countable infinite set, they are all projections. That's information which this gives. But now you might think about what happens if you change a natural number by rationals. There is equivalence. There's a corresponding result, a much deeper result due to Devlin. But I will not go to that. That's where the structure is. We go towards cardinalities. Although surprisingly, these are very, very close related. Okay, in the set theory, we have this notion of a large cardinal, so negation of it is accessible cardinal. And you will see most of the large cardinals which we consider in set theory have the property of cardinal omega, which was needed for Ramsey theorem. So therefore, essentially any large cardinal that we know will have corresponding results of Ramsey and Todorcevic. So the question is what happens by the accessible. And there are, of course, some counterexample for the reals as a cardinality. Real as a cardinality has a counterexample. But reals with a structure is not a counterexample, for example. Reals with a Borel structure is not a counterexample. That's another quite different area of research, and we'll note. So you would like to see is there accessible. So this is one of the things which was rather difficult for me when I started to realize. So you see, from the counterexample, for example, number 2, you realize there's nothing you can do there, or some other, for example, on the cardinality continuum, or then you will be asking, okay, so there is no analog of the Ramsey theorem itself, meaning that these equivalence relations with finite quotients don't have one element basis, but do they have a finite basis? That was actually a crucial question, the right question. In other words, there are counterexamples to Ramsey theorem, but can you classify them? This was a very vague question many years ago, almost rather question which was very much uninviting. for research, because you would expect you're asked to classify structures which are too complex. So that was the right question. For which index sets you can find a finite Ramsey basis? And of course, you can also ask, saying, for which structure there is a finite basis, even in such a simple power. The most simple power is the two-dimensional, right? In dimension one, there is not much. This is in Pidgeot principle, so there's nothing much happening in dimension one. So the first non-trivial is dimension two. Okay, so this is the very old result of Erdős-Hajnal and Rado, which they actually did not state it this way. And it is a positive answer, and it's a rather interesting positive answer. In this very strange cardinal, very relatively large, though still accessible. Still accessible is not so bad. I mean, depends what is bad. I mean, not so far away from. What is interesting in this, when you put it in this way, this answer is the fact, not only that the equivalence ratio have a finite basis in any power, but there is a finest equivalence ratio. All of them are coarsening of that. That's a rather new phenomenon you would not expect. You're expecting to classify, you like to have a finite list, while you're having a much more. You're actually getting a one equivalence ratio, so all others are coarsenings. This was later crucial in this connection with topological dynamics, which we found with Kekris and Pestov. This is actually literally what is happening here. You have this equivalence relation here corresponds something which they call universal minimal flow, the universal object. So there's in the commutative sense, there's a universal equivalence relation in this. Okay. Okay, now we go to the index set omega 1. That was one of the index sets which tend to show up more frequently in the problem which people ask. I mean, even though these index sets, because at present stage in mathematics, usually people ask about uncountability, just without actually specifying which cardinality. When somebody asks you something about uncountable objects, they typically asking you something about the first uncountable object. So that's why this particular case tend to be very frequent. And there is one equivalence relation discovered by Galvin-Hajnal, Sierpiński first and Galvin-Hajnal. Let me explain you. It's a very simple. It's rather at this stage ad hoc. They put, you have, of course, this is the index set of our first uncountable cardinality. We took it to a set of countable ordinals, for example. The moment you think about omega 1 as a collection of countable ordinals, you have this ordering, usual ordering, or between ordinals. But you can also import it, some ordering from the reals by some bijection and some other orthogonal to it. It happened to be at this stage here, this ordering was not known. This actually ordering was known 2 or 3 years after, although it was observed much. So there is indeed quite a different ordering than the first two. And Galvin-Hajnal was taking advantage of this to construct the equivalence ratio. Basically, equivalence ratio is telling you the two pairs, two unordered pairs are equivalent if only if they behave the same way to the three relations. And it's interesting again. It has this property of this result here. It has this. It's a possible candidate for that. It's a possible candidate for this universal object. It's irreducible, meaning that you can't reduce its quotient space more than there's four classes. You can't reduce it more. That was the problem which I started exposed actually by Galvin. Galvin was exposing me this problem. So I was playing with this problem and getting and noticing that actually this problem solves just about any problem known at that stage. So these I found in my notes working on the problem. Basically, solves lots of the problems. For example, about the continuum, about basically any. If you have a topologically representable graph, this cannot be wild. I mean, in a sense, should have a clique or a discrete sets. Linear ordinals have a five-element basis. The number 4 was interesting. Number 4 was actually, this is not so well known. The basis problem for topological spaces was really first considered by Sierpiński in 1920s, actually. He's for example, this relation here and this basis problem for Hausdorff spaces are very close related. So I was simply, I was realizing that actually, once you know that this is the universal equivalence relation, then you can very easily find actually three. What are the three spaces? These are discrete, the metrizable one, and so-called arrow space. You are taking the half-often intervals in the real line. So that these spaces, any Hausdorff space will have to contain one of these. Essentially reading the original Sierpinski's. There's another one in the context of the graph. You have a so-called forcing axiom. At that stage, basically, if you have a coloring or a graph, if in some forcing extension you have a clique or a discrete set, then you have it. Some kind of absoluteness between the. In set theory, this is very well-known phenomena, and which has been later formalized at the context of called generic absoluteness. But that was actually maybe the first instance of a. So basically, if one solves if Galvin-Hajnal translations is the worst possible or the most complex, then you basically have all these answers. And that's where the methodology of minimal walks. Methodology of minimal walks was made in order to actually construct different objects than the Galvin-Hajnal were considering, or at least to see whether there is something more there. Okay, for non-experts, we think about the ordinals in the von Neumann sense. The ordinal is a set of its predecessors, so we have these. Although this is more than just, you have this analog decimal representation, every ordinal representable as the finite sum. In this phrase, this is not very much useful if alpha is very large, because this alpha 1, alpha 2, there is no relationship between them and alpha. They can be some of them equal alpha. So, but still, this is a useful form. And there is an ordinal where this actually makes sense, this epsilon 0. I wanted to mention the classical notion of a walk, which people do in proof theory, analysis of the. So below epsilon 0, there is a very nice way or fundamental way to choose the sequence converging to an ordinal. You simply look at the counter-normal form, and then you choose inductively on the normal form. This particular choice was the one that was chosen by various people. I think that this one is probably chosen by Weiner. They call this an ordinal notation. And this is the way of a walk they're interested in. You fix an n, you take alpha, you go to the nth member of the sequence which converges to alpha, and then n plus 1 and n plus 2, etc., all the way down. You're moving down all the way towards 0. Eventually, this is going to end up, and it's rather interesting, that the place, how many steps you end up is it's a rather hierarchy which Hardy was considering long ago. And this hierarchy was rather useful because if you are moving alpha to epsilon 0, you are going to get a collection of functions which are probably total in piano arithmetic. So this is really quite, if you're analyzing consistency staying to piano arithmetic, these two results are very much important. Why? Because you are moving hierarchy questions to a combinatorial questions about these walks. And indeed, if you go to the shortest proof, say of Paris-Harrington theorem or various Guštein's theorem, are going to analyze combinatorial analysis of this. So that was the walk which was known before I was looking at this. And this is the walk which I decided to do. So instead of, I take the minimal step in some sense, and I don't walk towards 0, I walk towards some particular alpha. So in some sense, the minimal place on top of alpha. This could be equal, in which case the walk stops. And the minimal walk is simply you're continuing this procedure all the way until you reach alpha. The end is alpha, not zero anymore. So the necessity for this is as follows. You see, previously you had to analyze the consistent strength of the Peano arithmetic, you need to understand epsilon zero. That's from Gensen's theorem. In order to understand omega 1, you have to understand it. You have to understand it's a two-dimensional structure. You have to understand these functions. If you want an alpha beta or a various characteristic, which I'm going to see. So, in other words, omega 1 is a two-dimensional object. It's exactly two-dimensional object rather than a one-dimensional. So that's why there is alpha and beta you're working from. Okay, so here are some characteristics. They are in some sense the most obvious you can think of. You want to code. So you simply put the sequence of integers which you accumulated. So n0, n1, n2, etc. You simply code from this full code, you know the walk. So it's a function from a pairs of count ordinals into a finite sequence of integers. So you're moving from omega 1 down to omega, to a countable object, to rationals actually. So that's the most obvious code. So I'm pressing in the wrong direction. And there's another one, the largest weight. So these all, I was writing maybe not so, maybe a little bit too formal, but I guess the word simply largest weight. I mean, simply the largest integer which you see. This is this row 1. The reason for this is because this is actually, the point of this is actually quite general. This works just about in any context, that's the point. And the length. So I decided to test, to say something about these three characteristics. You have a full code length. You see, you have a full information about the code. You're losing a little bit, and you're losing much more. You're getting just a length. There's a number 3, row 3, which is actually losing much more. You're simply saying that there are two values, alpha 0 or 1, where the last step is largest or not. So I'm not going to state this because. So there are these three very simple characteristics. And they're all functions. The point is that the important thing is that they're all of the following sort. Some countable index set, in all the typical omega, and these are finite subsets. But I'm going to think about as ranges. So this is okay, here are some properties. If you make this usual interpretation via continuous function, then this von Neumann inequality, you see, von Neumann was identified better with the processors. And here you identify better with the increasing sequence of rationals, meaning that this function is actually increasing. Not difficult to see, so you are connecting omega 1 with the rationals. And row 2 is somehow what you are really doing. You are trying to enumerate omega 1 in the order type omega, which is of course not possible, but at least you are getting very close to what's possible. So you are basically finite to 1 for fixing beta, you are finite to 1 below beta. And at the same time, for a different alpha beta, you have only finite errors. So somehow you get it. And row 2 is again unboundedness. This is a rather interesting. You have unboundedness on the rectangle. In other words, there is arbitrary long. If you have a two unbounded subset omega 1, there is arbitrary long walk from beta to alpha, from when you choose beta in B and alpha in A. So kind of. On the other hand, on the local level, they are bounded. So they are the distance between these two fibers is finite. This comes from analog of this for the row 1. And there is the deepest one, which perhaps I will not say very much, but I would like to say this is because in some sense why there was one of the reasons for a large number of applications of this theory is exactly this some sort of adding a little bit to the algebra to you're adding a little bit of a metric structure or actually really these inequalities to analyze the omega 1. As a matter of fact, this actually can go much higher. And I just mentioned just how far. So it's perhaps not pointless for me to actually explain why you're doing this. You're doing this to achieve these metric conditions. So you're doing the most natural thing which you need to achieve. But the point is that this definition is actually much more general if you plug it to a longer ordinals. And I just give you some particular, I guess, sense of why would you want to do that. Some application to so quite well-known problem in analysis, unconditional basis sequence problem, which was solved by Gowers and Murray. And they were asking us how sharp are their results. Again, so unconditional basis sequence is in a norm or Banach space is some sequence where the summation doesn't depend on the order, which essentially means that the projections are bounded uniformly. It's very natural. You get a much more structure when you have such a sequence. And the question is, does every norm space or Banach space have one? The answer was negative. Gowers-Murray got a counterexample, a reflexive counterexample. But the more important than this, that example was inspired Gowers' dichotomy, which says, indeed, existence of infinite unconditional sequence is actually just a part of the dichotomy. The other part is so-called horizontally indecomposable space. And we know that these spaces that you can't decompose in, and no infinite dimensional subspace can be decomposed into two proper infinite dimensional subspaces. And this phenomena is a phenomena of small density, of cardinality continuum. So they asked us how far you can go with this. And this is where this distance function was crucial. Actually, you can actually go to LF1, and as a matter of fact, if you go to weakly null sequence, you can go all the way to omega to the k high dimensions. And here we achieved something optimal, because in this context here, this is the largest context you can go. So the unconditional basis sequence has its invariant, and invariant is the first limit ordinal, first limit cardinal. So that's one of the application of higher dimensional version of this algebra here. This is a side remark, so we go back and continue. Okay, so now, as I said, we want to study. Okay, so I was giving you some definition of minimal walk, and I got three characteristics, and I was saying, well, maybe and the context is, and the hope was that you're getting canonical objects, right? That was the hope. So now we would like to examine this, where we really did get canonical objects. So I say, okay, let us study this kind of objects. Class of all such objects, and see what did we get. And this is that every such object has a tree. As a matter of fact, can be identified with this tree. And you will see that all these trees are, for example, to the Koenig's lemma. They're called armchair trees. For example, to the Koenig's lemma on this context. You're simply closing off downwards the fibers. And there is a distance function, the minimal place where they disagree, which is usually ultrametric, which you only say, or in a counter set, this would be corresponding with actually a inverse of the ultrametric. I mean, you have to divide by this, but anyway, we are not interested in that. And that's one of the crucial observations in all this stuff, that the characteristic which I was obtaining using mode, they have this very strong metric property, Lipschitz property. That these trees have a lot of self-Lipschitz maps. So suddenly there is a property, intrinsic property of them, which is basically maybe is what is really saying. Just one picture telling you everything. This is probably difficult to see. You know, you have these such a trees, and you have a say level preserving map, and you have another. The distance is the place where they disagree. This is basically saying that there's a profusion of a Lipschitz mapping. These heights are the same. The length and the distance are the same. And this is on the next part of the slide. So distance is the same. Image and domain distance the same. So it's a crucial property. Every of the characteristic have it, and there is another property. So Lipschitz property is one of them. The other crucial property is metrically equivalent. Basically, this geometric, the trees are, of course, the tree has its usual branching, etc. What matter is the distance, the correspondence between the distance between beta and gamma and some other. So say something. This has to be the corresponding distance structure is copied, as basically saying. Metric equivalence is another characteristic function property which I obtain. And the corresponding observation is that Lipschitz characteristics are metric equivalent. And there is a Martin axiom, some version, very formal. I will again. Okay, so here is some explanation is needed. You see, we are constructing the object. We know that many of the questions which we are considering are very much sensitive on the independence phenomena. We are interested in a canonical object, in particular objects which do not depend on the axiom of set theory. So therefore, where they are to relate them, or to ZFC object, to relate the object which you obtain, just you're allowed to use some bare category principle or some Martin axiom or something of that sort. Of course, you can also do corresponding theory of generic objects, which is a completely different setup. Here we are interested in the object existence of the canonical objects whose construction do not involve additional axiom of set theory. So therefore, the comparison have to be done using them. And here the global theorem, which says that basically here's first observation, there are characteristics which I was showing you, they're all Lipschitz, all metrically equivalent with a little bit of a Martin axiom. Moreover, there is really only one tree. And moreover, the equivalence class of this tree, this is a shift, this equivalence between the trees you can embed. You see, a tree is a structured, so there is a embedding, there's a strictly increasing. If you write like this tells you there is a strictly increasing map from this into that, or there is a Lipschitz map from this into that, if you like, which is the same. And of course, equivalence is even if you have it in both ways. So there's that equivalent. So every pair of Lipschitz characteristics are equivalent. Modular shifting. This shifting is interesting. It's a discrete shifting, actually, meaning that tip TA plus 1 exists and is immediate successor. This is actually immediate successor. So indeed, they do behave like ordinals. There's nothing in between. So there's one tree. If you shift it, you obtain all other such trees. And what is surprising, this last one, even though it's fit, this class is, of course, sigma 1 definable without parameters, and at the same time generates every other, for example, to the Koenig's lemma, every other arbitrary tree. So in other words, the three characteristics of the walk, actually, any of them, would generate you all class of arbitrary trees. And even the corollary telling you that even though, of course, there is a parameter in the definition of a walk. Parameter of and now it started working. Perhaps see there is a parameter here in the definition of the walk, and now of course you might say, if you want to have a canonical object, it should not be depending on the parameter, and indeed we have such a situation. No dependence on the parameter. Of course, it's a class, it doesn't depend on parameter. So in other words, there's one canonical tree. You can take arbitrary one, like say T rho 0. And there are no other, at least if you're working ZFC. Okay, so there is another concept, considerably deeper, is this oscillation. You are looking natural upper trace. Of course, in this walk, every walk has its trace. And you would like to see how these traces oscillate, basically how many times they intertwine. And the corresponding mapping happens to be an interesting mapping. You have to be a little bit careful. I wrote here, 0 referring to the T rho 0. You can put arbitrary one, actually. So you are basically oscillating in the metric sense, what you're really doing, you're walking from alpha to this ordinal and from beta to this ordinal, and see how many times they intertwine. That's the mapping. That's oscillation mapping of the upper traces. It's happened to be this distance function happened to be a success ordinal, so minus ones make sense. And there was a new canonical. There is an object which tells you this Galvin-Hajnal list was not complete. So that was actually the reason for invention of the walks, to show the Galvin-Hajnal list translation is not the universal one. So we have also these counterexamples to the basis problems. Okay. You get this. But of course there are other basis problems. For example, for linear orderings. So you like to look at the canonical linear ordering. So this is basically, what is this? You take the fibers of row 0 and you order the Lesigash. You get ordering on omega 1, which has again similar properties, a canonical object. It has this I hope some can be heard. Yeah. Okay, so there is that property first discovered, asked by Countryman, and answered first by Shelach. Actually, had such a phenomenon was discovered by Shelach. Although here we have this property without actually looking for it. So we have this property that this Cartesian square are rather unusual if you think about if you think of linear ordering as a squares and a product of, say, L and L. Somehow you always think there is this second diagonal which doesn't exist actually. Tells you that actually the whole square is union count many chains. So there's a decomposition into count many chains. That's one of the objects, and it happened to be canonical in a sense that every other object of that sort is related to it. There's a strictly increasing map. There's an injection from one into another. There's a isomorphism, strictly increasing map. Isomorphic embedding, I guess, in the context of linear orderings. Again, there's that sigma 1 definability. Again, here the sigma 1 definability is without parameters. And Justin Moore was actually showing that this, you see from the previous slide, it tells you that from number 2, it tells you that this is a minimal uncountable linear ordering. So if you are solving a basis problem for any class of uncountable linear ordering, this has to show up on the list, and that's actually what is happening here. You see, yes, yes. Which one? Yeah, sure. I forgot. Yeah, I have to flipping. I said it on the next slide. Right. I slid it on the next slide backwards. See? Okay. You're quite right. You have to put here K or its reverse. So identify the ordering with its reverse. Basically, you have a 2. Yeah, thanks. So this is okay. So what is happening here? You have a omega 1 and omega 1 star reverse. You forbid this, and you forbid separable linear orderings. You get a class of uncountable linear orderings, and it happened to be that there is a basis of size 2. The previous work was done. The previous work done by Baumgartner, which was taking care about separable orderings. So you have a basis 5. Here we have 5. You have 5 of the orderings. And there's a further work where actually you want to consider class of all such orderings. You forbid Baumgartner's ordering, separable ones, and you forbid omega 1, omega star. You get some class of orderings. You can call it a class A. this class, see, happened to be a rather interesting class. It's a well quasi-ordering. It's a complete classification of it in a sense that they behave like ordinals, rather similar to the class of the trees, rather similar to this shifting, although not quite, actually, it's even better in some sense. So this is, of course, theory well quasi-ordered set is very well known, and old theory which started from the 1940s. One of the most quoted result is Laver ordering. The current Ordinal orderings have this property, and that was the former student at U of T, Martinez Ranero. Okay, so here is another variation on the trace. So there is this upper trace has its mirror image. Upper trace has its mirror image, namely downwards. So which is called lower trace. So these are the finer pieces which are left out of these. They don't need to. You see, these are going in order towards alpha, while these might start in some way. So you are really collecting. You're only collecting the one which are coming closer to. Of course, they will never get as close. Oscillation of function for the lower trace is the definition of Justin Moore. This is his definition of oscillating on the lower trace. Again, there is a O1 saying you are doing row 1. You could do other things. It's a very natural. It is not any oscillation of sets, but of functions. And this is the new information. New information that this oscillation is mapping behavior is complex even on rectangles. Synthetic means that they contain arbitrary long intervals. And that was, and that's itself solved the other problems, basis problem for the class of spaces, regular spaces, very importantly. Regular spaces do not have a finite basis. There is that complementary result to number 2 that actually the switching Hertel-Lindelof and separable is possible, while there is quite a surprising discrepancy between the two. And I repeat this. You see, so far what was left is that this result. Whenever you are disproving a sum basis problem, what you're really doing is simply closing off to the real problem, finding upper lower bounds. So what was now left are the first countable spaces. It's actually a very attractive conjecture or question of Fremlin, which tells you how the class of complex spaces should look like, as long as you are not using additional axiom to construct them. So basically, any compact space either should be metrizable, perhaps, well, the number 2 is, in number 2 metrizable comes, but okay, it's either metrizable or it's a, so either uncountable discrete subspace or it's a 2-to-1 preimage. So number 2 is interesting in some sense because it somehow behaves like a discrete interval. And this current conjecture is that actually you will never find anything more complicated than the split interval. And this previous problem on the first countable space is essentially equivalent to it. And there is an indication in the Borel world that this is correct. That was the paper Justin just mentioned in his introductory talk. So indeed, when you test this question on the naturally representable space, for example, of course, every compact space is subset of Tikhonov cube. If the index set is a Polish space, separable metric, complete, and the corresponding functions are Borel, in this case, Baire class 1, actually. You can put a Borel, but you have then assume that K is separable, which is not a big assumption. Then actually you have to, as a matter, we can even do more, saying that if it is not metric, then it actually contains a copy of this one. It's a very strong indication that Fermi's conjecture is probably correct. And here is the last subject, canonical ultrafilter omega 1. This comes from this metric structure. So there is a surprising, you see, you take arbitrary characteristic, you have this distance function, and you look at, for every set, look at the set for distances, non-trivial ones, I mean, not infinite. And it turned out that this Lipschitz condition is essentially the same as saying that this generates a filter. You know, if you look at the typical metric space, you know, in the ordinary sense, you'll never get this. You'll get always a different subset, even large one, where distances are very different. Here you have a filter. And so you have a uniform measurement of your filter. For every Lipschitz characteristic, you have a uniform, corresponding uniform filter. Okay, so this is a possible canonical object. Let's see where it is. And indeed, it is. It says if you have number two, one is a bit surprising, because if you get a filter, of course, there are lots of uniform filter on omega 1, say co-bounded filter of a co-bounded set. So, but here actually you get a ultrafilter, the maximal. You get a maximal filter. And you get it from an assumption which is not a typical your assumption for constructive ultrafilter. In this area, you are constructing ultrafilter by assumption that some characteristics like M is equal to the continuum, not that is not equal to the minimum possible value. It's a different setup, you see. So, and here is telling, number two is basically telling you this metric structure which we were talking before. Ultrafilter is actually characteristic. This is equality. You're reducing equivalence relation to the equality relation. This is you are so-called solving this problem of invariance. Yeah. Ultrafilter is a correct invariant. And here is in the theory of ultrafilter, there is a natural Rudin-Kistler, meaning that there is a bijection, there is a permutation of the index set which moves one to another. This is RK, Rudin-Kistler. They all basically, this is basically one single ultrafilter, modulo permutations. And this ultrafilter is a sigma 1 definable, and for example, again, rho 0, you can take a sigma 1 definable. And again, there is no dependence on the fundamental sequence you choose. And now we want to simply project this ultrafilter from index sets omega 1 to a countable one, because this is sometimes a more frequently used. Ultrafilters on omega are probably more frequently used. There's a notion of a selective ultrafilter. I'm not so sure this is the right name for it, selective at this stage, but okay. So I just remind you, we have this arbitrary characteristic. You have a ultrafilter on omega 1, and you are simply projecting it down to, this is the projection f of a, projecting it down. The usual way you move measures from one index set to another. There's nothing happening. So you have so this is to summarize. Before we have this AVO, it could be principal, of course. This is a ultrafilter, which is a sigma 1 definable from, of course, these parameters, f of NA. Because this is not maybe not that much interesting because you are defining the parameters, maybe they are as complex. We'll see actually that you can get rid of parameters. But let us first ask which kind of ultrafilter is. You have a definition of ultrafilter. Sigma 1 means only one quantifier. You are defining only one non-trivial quantifier. It's very simple, but sometimes it's the simplest possible complexity. And you're defining a maximal object, almost contradictory. I mean, you know, if you know a little bit about if you know that ultrafilter on omega is never measurable or proper to Berry, you will see that, and therefore is not analytic. You consider this rather surprising. And it happened to be selective, and selective is not the right word because it said the selective is the right. Every mapping is either constant or one modulo this ultrafilter. So in other words, what is this telling? That's really, again, the Ramsey theorem shows up. So another context when you did not look for it, Ramsey theorem shows up. This is the Pidgeot principle, of course. But Pidgeot principle modulo ultrafilter. And here is one theorem which actually shows that these ultrafilters are selective, or I think the right word would be a generic or a Ramsey ultrafilter. It's really a generic one. It's the most generic ultrafilter you can think of. It's a ultrafilter you obtain by a forcing over say, model of the get a constructible universe which contains reals. So if you have a large kernel around, you select every selected ultrafilter is. And it happened to be correct. So any of these images, either is principal, in which case obviously selective, I guess. But if it is non-principal, it is generic over this. You're constructing generic ultrafilter and you're defining it. And here's the general fact that now we would like to get rid of the parameters. So that's why we need to compare arbitrary. We need to compare them. It turns out that they are the same, modulo permutation. And now you will say you don't like this f moving from omega 1 to omega, so there's additional parameter. It turns out that in the original definition of characteristic rho 0, rho 1, etc., you don't need this map is already given to you. This is simply a distance to the set of limit ordinals. Distance to the set of limit ordinals is a good enough map. And that's a fine result which says actually we have a canonical ultrafilter on omega. It's a selective. And it's a sigma 1 definable without parameters. Its class is sigma 1 definable without parameters. So we have a canonical generic ultrafilter. And I finish with this. Thank you.
Thank you very much. Are there any questions? Okay, well.
Maybe it was too fast, or
Too fast for me, but
yeah, sorry, I mean too much. Okay.
Thank you very much, and we would like to investigate with the this is not actually a bag of points. We would like to present you at the same time with a bag of Fields Institute gear with their very fashionable 20th anniversary logo.
Okay, thank you very much.
Thanks, David.
Thank you.